Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the slip speed control. We are changing the frequency, we are changing the voltage, but we are regulating the slip speed. Now, when we are regulating the slip speed with the increase of the per unit frequency, that is k, the various parameters are varying as follows. So, the torque is initially maintained constant, this is the torque initially maintained constant, and then this is called constant torque region. Current is also maintained constant, the power increases and the slip frequency is also maintained constant, is nearly constant here. So, the region between 0 to 1 per unit, this is the per unit frequency, per unit frequency. So, when the frequency reaches the rated value, the torque is the rated torque and the current is the rated current, the power increases and reaches the rated value of power, the slip speed reaches some value and after that we enter into constant power region. So, the torque reduces, this is the torque reduces, power remains constant, this is P m. The current is still maintained at the same value I s, current does not change. So, the current is almost the same and then the slip speed has to increase. The slip speed increases linearly till we reach per unit frequency, which is 2 per unit. Now, after that the slip frequency reaches a maximum value, the slip frequency remains constant and the power decreases, the current decreases and the torque further decreases. And this is called constant slip speed region, because the slip frequency, which is omega S L here, is constant, the power decreases, the current decreases and the torque decreases 1 by k square. So, all these things can be easily obtained from the equation that we discussed in the last lecture. So, we have primarily a constant torque region, constant power region and constant slip frequency region. Now, how can we implement this in a closed loop fashion? So, we are still having a constant volt by Hertz control, but we are having a slip regulation. Let us see the closed loop block diagram of constant volt per Hertz control with slip regulation. Constant volt per Hertz control or VYF control with slip regulation or slip speed regulation. The closed loop, we have to draw the closed loop block diagram. So, let us start with the reference speed. So, we have the reference speed that we feed here and this is fed to a summer block, which is having positive and negative, and the reference speed is compared with the actual mechanical speed of the rotor and this is fed to a PI controller. The output of this comparator is fed to a PI controller. So, this is called a speed controller as well, and the output of the PI controller goes to a limiter. The output can be very high, so we have to limit the output. So, the output is limited. So, we call this to be a speed controller, and output of the speed controller is slip. So, this is called slip limiter, slip limiter. We are limiting the value of the slip or slip speed limiter. The output of the speed controller is usually the slip speed, because we know torque is a function of slip speed. If we want to increase the torque, we increase the slip speed. If we want to decrease the torque, we are decreasing the slip speed. So, our key variable here, key control variable here is the slip speed. If you want to increase the current, increase the slip speed. If you want to decrease the current, decrease the slip speed. So, when we limit the slip speed, we are basically limiting the torque and current. The output of the slip speed limiter is the reference value of the slip speed, omega SL. Now, this is added with the rotor speed, the electrical rotor speed. So, we have to multiply by a factor of number of pole pair. So, this is omega m here, and this is omega r. Omega r is the electrical rotor speed. When we add this omega r with the slip speed, we get the synchronous speed, which is omega s. So, this synchronous speed or omega s is the electrical variable. So, this goes to a function generator. So, what we have here is a V by f function generator that we discussed, that we have discussed earlier. So, in this case we have the V by f function generator. So, something of this sort, beyond the base speed the voltage remains constant. So, this is voltage and frequency in the x axis, voltage in the y axis. So, the output of this is a voltage V star. Now, this is the reference frequency, the frequency command is here. So, we have the reference frequency omega s in radian per second, and then this goes to an inverter. A voltage source inverter. The input of this inverter is a DC voltage, the output is the inverted voltage. So, what we have is an induction motor here, and the inverter feeds the induction motor. We have a speed sensor which is connected to the induction motor, maybe a tacho generator, that basically gives us the mechanical speed. So, this is the speed sensor which gives us omega m, the mechanical speed, which is fed back in the input, as well as to calculate the synchronous speed, we add the rotor speed with the slip speed. So, slip speed plus the rotor speed is synchronous speed. So, omega s is equal to omega SL. We are doing everything in terms of electrical variable. So, omega s equal to omega SL, the slip speed, the electrical slip speed plus the electrical rotor speed, and that is equal to 2 pi f, the frequency. So, when we want to change the synchronous speed, that is omega s, we have to change the frequency. So, this information is also the frequency information. The omega s star is also the frequency information. This is the voltage amplitude. So, when we have voltage amplitude and frequency, you can feed this to a voltage source inverter with control. So, the control is also here, and the output will be the voltages, 3 phase voltages, which are fed to the stator of the induction motor. So, this is a constant volt by Hertz control with slip regulation. The advantage of this drive is that this is a closed loop drive. we have a closed loop feedback, there is no instability, and also we are limiting the slip speed. By limiting the slip speed, we are also limiting the torque as well as the current. So, the current of the motor cannot exceed beyond the rated value. Now, after this, let us discuss about the multi-quadrant operation of an induction motor. Induction motor can operate in various quadrants. It can operate in forward motoring, forward braking, reverse motoring, reverse braking, just like a DC machine. But we need to have two converters in this case, one at the motor side, the other as the input side, that the AC side. The supply frequency or the supply is an AC source, the motor is an AC motor. So, we have to have two converters here. Let us try to discuss about the multi-quadrant operation of induction motor. So, what we have here is the following: we have two voltage source inverter, we call this to be inverter 1 or converter 1, or let us say this we can call as AC to DC converter, and the second stage is called a DC to AC converter. We can call this to be a converter 1, this is called converter 2. Now, these two converters are connected in the DC side, and there is a DC link capacitor here, and this voltage in the DC side is VDC, the DC link voltage. So, the output of DC to AC converter is AC. So, we have the induction motor here, which is supplied from this DC to AC converter. So, this is a 3-phase induction motor, which is being fed from the DC to AC converter, that is converter 2. What about the fast converter? The fast converter is supplied from the AC supply through some inductors. So, we have the inductors in each phase of the converter, and the input in this case are 3-phase ACs. So, we have a 3-phase supply with neutral, and this is the inductor here, LS, LS and LS, and the input side has got the voltages. The voltages are the supply voltage in phase A and supply voltage in phase B and supply voltage in phase C, VSC, and the current which goes here into this is ISA, phase A current, this is ISB, and this is ISC. So, the second converter could be a V by F converter. So, we can go for V by F control here. Okay. The first one has to be controlled such that the DC link voltage is kept constant. Now, when the motor goes into the motoring region, the power is taken from the DC side to the AC side. So, this is for the motoring. So, the capacitor discharges, since we have a capacitor here, the capacitor discharges in the motoring region, because the power flow in this case is from the DC link to the motor. Now, for the braking operation, the power flow in fact reverses, this for the braking. So, when we go for the braking, the power flow reverses, the motor works as a generator and the power flow is basically from the motor to the DC link. So, the voltage in the DC link increases. So, what we have to do here, we have to monitor the DC link voltage. So, DC link voltage is being monitored by a sensor. So, what we do here, we use a sensor in this case and we monitor the DC link voltage. So, DC link voltage is being sensed by a sensor and this voltage is fed back, and what we have here is a comparator, is basically a subtractor here. So, we want to maintain a reference DC link voltage which is VDC star. So, this VDC star is compared with the feedback voltage, that is VDC, which is obtained from the DC link by means of a sensor, and the error goes to a controller. Error goes to a controller. This controller processes this error and gives the signal to converter 1. So, this is the error of the DC link. So, if the DC link discharges, it is motoring. So, the error is positive, and if the motor is under the braking region, the DC link voltage will increase. So, this error will be negative. So, E will be negative because VDC will be higher than VDC star. Now, by sensing this error, this controller will make the input power either forward like this for motoring or reverse for braking. So, the power flow is basically reverse from the input side. This is the power for the motoring and power for the braking. Ultimately, the power comes from the AC supply. We have AC which is converted to DC, then we are converting that DC to a variable voltage, variable frequency AC. So, if the motor is operating under motoring region, power is coming from the source. If the motor is undergoing braking, the power is returned back to the source. This is called regenerative braking. So, what we are talking here is regenerative braking. So, this is for the braking condition, the power has to go back to the source, the power flow has to reverse, and for the motoring, the power has to be from the source to the motor in the forward direction, and motoring and braking are identified by the DC link voltage. If the DC link voltage increases, it is the braking region or the braking condition. If the DC link is decreasing, it is under the motoring condition. So, accordingly the controller will give the triggering signal to converter 1, which is a AC to DC converter. Now, let us draw the phasor diagram. Now, here we have the inverter phase voltage. This is VSA, VSB, VSC are the source phase voltages. Now, the inverter voltages are VIA, VIB and VIC. So, we can write a vector equation. Now, if I say that Vs is the source voltage, the source voltage is a phasor, that is equal to the drop across the inductor. The inductor drop is j omega Ls into Is. Is is a phasor, that is the stator the input current, plus Vi is the inverter input voltage here. Now, in this case Vi can be obtained as Vs minus j omega Ls into Is. So, this is a AC to DC converter, or we can say this is an inverter which is converting DC to AC. So, we have to synthesize VIA, VIB, VIC, which is Vi in the form of a phasor. So, Vi can be obtained by taking this Vs minus j omega Ls into Is. Let us draw the phasor diagram. The phasor diagram can be drawn in the following fashion, that we have the input voltage which is V s. Now, we want that the power factor has to be unity. So, what we say here that power factor in the input side should be unity, should be 1. So, which means the current should be in phase with the voltage. The input current and the input voltages are in phase. So, this is our current I s per phase, and we have the voltage here, that is also V s. So, they should be in phase. So, the input voltage and input current should be in phase. Now, let us take this vector equation. So, V s minus j omega L s I s. So, what is j omega? J omega is a rotation by plus 90 degree, minus j omega is a reverse rotation. So, this is minus j omega L s I s, and if we add these two, we get V I. So, this is the power flow from the source to the load. This angle is called the power angle or the torque angle. Okay. Now, this is for the motoring condition. Now, for the braking, the power factor should be minus 1. So, power factor should be 1 for motoring and power factor should be minus 1 for braking. For braking condition, because for braking the power is negative, which is the flow into the supply. So, in this case if we make the power factor minus 1, this is our voltage, the current should be in opposition with the voltage. This is 180 degree and cos 180 degree is minus 1. Now, here if we say that minus j omega L s into I s. So, this is minus j omega L s into I s. So, if we complete the phasor diagram here, we get this is our V s minus j omega L s I s, this is V I, and this angle is the torque angle which is delta. So, this one is for braking condition. So, we have the motoring for which the power factor is 1 and we have the braking for which the power factor is minus 1. So, the idea here is that we have to synthesize the inverter phase voltages and accordingly we should control the voltages of converter 1. Let us see how we do that by means of a block diagram. So, we go for a control block diagram. So, we are planning to keep the DC link voltage constant. So, that is our reference value VDC star. So, this we compare with the actual DC link voltage. The error is fed to a PI controller. And then we feed the output of the PI controller to a limiter. So, this limiter will limit the output of the PI controller. So, this error basically gives an idea of the current. So, the current magnitude is decided by the proportional integral controller and the output of the limiter is the peak value of the input current, which is ISM. ISM is the peak value of the input current, peak value of input AC current. So, if we want, if the error is more, the current is more, if the error is less, current is also less. So, the error is a measure of the current. So, depending on the error, the current is given out by the PI controller. Now, this current is multiplied with a value which is sin omega t plus pi by 2. We have a phase lock loop from which we get this omega information. Omega is the input supply frequency, plus pi by 2 we have a phase difference of pi by 2. Basically, what we are simulating here, we are simulating this j is a rotation by pi by 2 and we have a negative sign here. So, this is a multiplication, then we multiply with the reactance is omega L, and then we feed this to again a subtractor, we have a minus sign and plus sign. Here we apply VSA. What is VSA? VSA is Vm sin omega t. We can have a sensor to get this voltage, input supply voltage, which is VSA. This we can obtain by means of a sensor. So, we can use a sensor to sense this VSA. This VSA is sensed and is fed here. So, we are basically trying to realize this equation. Vs minus j omega Ls Is is Vi. Vi is the inverter output voltage here, the first stage. So, in this case the output here is phase A. Since we have 3 phase, we have to have 3 different control. So, this is VIA, the phase voltage reference of the inverter, and then similarly for phase B, we take the multiplier here, pi is a multiplier, again we have sin, but here this time this is omega t plus pi by 2 minus 2 pi by 3, because we are in phase B. So, phase B is again fed to the reactor, that is omega L multiplication by the reactor or the reactance value, and then we sense phase B voltage. Since we are having 3 phase, we have to control 3 phases of the inverter. So, phase B is being sensed. So, we have a sensor to sense the phase B voltage. Phase B is shifted from phase A by 120 degree. So, in this case we add here VSB, which is Vm sin omega t minus 2 pi by 3, and the output of this gives us VIB reference. And in a similar fashion, we have to get the C phase also. Now, for the C phase, this is sin omega t plus pi by 2 plus 2 pi by 3 for phase C. We again multiply by this reactance omega L, then we have a subtractor, and here we get VSC by means of a sensor, which is Vm sin omega t plus 2 pi by 3. So, out of the subtractor we get the reference for phase C, which is VIC. So, this VIA, VIB and VIC are the references for the 3 different legs of the inverter. The inverter can be operated with a sine triangle PWM. So, these are the 3 sine references for the 3 legs of the inverter. So, when the inverter 1 or the converter 1 is triggered, the input currents are controlled, and objective is this, that we have a closed loop control by which we are maintaining the DC link voltage constant. So, with the change of the motor operation, the DC link voltage is automatically sensed and the current is given as ISM. ISM could be positive for motoring and it could be negative, implying that the power factor is -1 for the braking condition. So, this is the control block diagram which shows how to implement this experimentally in a closed loop drive. So, the drive can operate in all possible quadrant. We have two converters. So, converter 2 and converter 1 are operated independently. So, depending upon the operation of the drive, we can operate in motoring, braking, both in the forward and in the reverse direction. So, thus we discuss the multi-quadrant operation of induction motor. So, we have to have two converters in this case. So, we stop here for today's lecture. We will continue with this induction motor drive in the next lecture.